This is the second video. Hi, of course. Good morning. This is the second part that we are going to talk about magnetic fields and magnetic forces. And the next one, like we did in the first video, we were talking about a charge. Now I will talk about a current. Okay, and then the first thing I'm gonna introduce is how we gonna represent the magnetic field of a straight current carrying wire. Okay, then simply I have a wire and I have current going through it, and I want to see how, okay, I'm gonna represent the field, the magnetic field created. Now I will say here, again, we are going to use the right hand rule, and then you are going to point your thumb in the direction of the current, and the rest of the fingers, they are going to be representing the magnetic field. Now I will say when you will do this, you are going to have the the points on top of the wire. They're gonna have the magnetic field enter out of the page. And when I talk about a point that is below, is gonna be entering, because what's happening here is I will say, if I will draw this on the other, let's say, draw it like this, and maybe try to have it like, you know, um, in 2 dimensions or 3 dimensions. Okay, if this is the current, I'm gonna have the magnetic field is gonna be um, as concentric circles like this around the wire. Now at any instant, the magnetic field direction is going to be the tangent to these. Then this is B here. Okay, now, okay, here behind the wire, it is like this. And I will say this is really the magnetic field created by this wire. I want to maybe also directly talk now about the force that is going to be affecting current that is in this conductor. Whenever we're going to have a moving charge, then we're going to have a force. And here, since we have a wire, I will say we will be able also to talk about the magnetic force on a current carrying conductor. Then here what I have a conductor. That conductor itself, it has its own current or current density, we can say. Okay, and then I will say, and it is immersed in a magnetic field. And let's assume my magnetic field here, it is into the page like this, crosses. And here we are going to find that what's the meaning of having a current. It has inside charges, and these charges, they're gonna move with a drift velocity vd, the drift velocity, And therefore, according to what we studied before, we are going like each charge is going to feel a force, and that force is going to be QV, okay, the velocity, times B, and that is actually here. This is VD, the drift velocity. Now, if I will say this conductor has a number of charges that can be represented. Remember, we defined before N, which is number of charges per unit volume. Then it is N divided by V. And if I want to represent what is N, the total number of charges is going to be N times V. For this type of conductor here, I will say it might be a good idea to say that this is its length and it has a cross-sectional area, then it is NA times L. Okay, this is the what is called the total number of molecules. Therefore, if I wish to calculate the total force, is going to be F equals total number of molecules times QVB, assuming of course there is 90 degrees between the between the magnetic field and V as outlined here. And therefore, I can have this NaLQVB. And if you still remember from chapter, I cannot remember which one, when we were talking about the current, we said that, just wait here, I forget always to say VD. Okay, then here I will say NaQVD all together times L times B, and that here is I, the current. This is the, do you remember we have like three formulas for or equations for calculation of the for the current, and this one is one of these. One more point here to say or to mention is that I will say the force again, because it's a cross product. The force is always perpendicular to both the conductor and the magnetic field. And we use here again the same right hand rule for a moving positive charge that we outlined in part A of this topic. Okay, then I will say if I have, let's say, B in this direction, and I have the conductor, the current is going, let's say this is I, and it is in that direction, which is, this is, let's say, my conductor here. Okay, then the force is going to be in a direction that is perpendicular to both. Okay, assuming these, let's say, assume these are along the horizontal, and then this one is gonna be the vertical. Actually, the more general definition, it is the force. It is I, the current, L across, yeah, this is, sorry, this is L and that is I, L cross B. And remember, any cross product here, okay, we use, okay, for the magnitude, F, it is ILB sine theta. And for direction, the right hand rule. I will show you now how to solve one of these problems related to, you know, like currents acting on here. A long wire carrying 4.5 amperes of current makes 90 degrees bends as shown in the figure. The bent part of the wire passes through a uniform 0.240 Tesla magnetic field directed as shown in the figure. It is out of the page and confined to a limited region of space. Find the magnitude and direction of the force that the magnetic field exerts on the wire. Here, I want to add a page, and I will say, let's first summarize my, things. B is out of the page, and it's like very helpful now to start saying in terms of what of the axes, then it is in the direction of the Z positive. Now F can be calculated as I, we said, L cross B, and therefore it is, we said, I, L, B sine 90. And if you look at the, the direction of the currents, the conductors themselves, for the first part, this one here, it is perpendicular, and the second, it is perpendicular, and the third, it is perpendicular. Therefore, here, theta is going to be 90 for all, and therefore is going to be IL times B. Now, I cannot do this in one calculation, therefore I need to find first FA, which is I times LA times B, and that is the first piece. It has a current 4.5, like this is the current is constant, and it has a length that is I'm not sure what's that because it's not written here. Okay, then here I'm gonna say is gonna be X, and this is 0.2 0.24, because this length was not given. Okay, 0.240 Tesla, and that is gonna be 1.08 x times in newtons. Now for the second part, B, FB, it is again I, L, B, B, B lowercase, so that I know that it's B section. And that is 4.50 amperes times 0.30 meters times 0.20. I don't know why I am insisting on having it. Okay, and the last one, it is 0.240 Tesla, and that is going to give us 0.324 in newtons. Now for the third part, I know that the whole thing is 60, and then this piece here, this one here, from here to here, is going to be 60 minus x. Okay, therefore, for C, I'm going to say IC is ILC equals B at ILC times B equals 4.5 amperes times 60 minus 0.60 minus x, because I need to convert into meters. And from that, I can get 0.648 minus 1.08x in newtons. We know that forces FA and FC are both in the same direction. How do we know? Because the direction of the conductor is the same and the direction of the magnetic field is the same. Then the current is to the right and the conductor, I will say, the magnetic field is out of the page and the current is to the right. Therefore, they're gonna have the force is gonna be in the same direction. Therefore, what I can do is I can add them, because when you have two forces in the same direction, this is what you can do. And from that, you're gonna see that the x component, that like, okay, the number that is multiplied is gone, is along, I will say y negative, okay, because we have B here and I, it is this direction, then I will say, you know, F is gonna be, this is the right hand rule. Now, the remaining one is B, okay, the FB is going to be, okay, it has the magnetic field into the page, right? Out of the page. And the current is upward like this. And therefore, the force is gonna be in this direction. Remember always the axes, and therefore, if I wish to calculate the total force, now I have two vectors, one of them along, let's say, the negative y, and one of them along the positive x. They are perpendicular to each other, and therefore, I can say it is FC squared plus FAC squared plus FB squared. And from that, I will be able to calculate what is really the magnetic force. Now this is here to calculate its magnitude, and that is 0.724 newtons, and I can find also its direction by determining the angle, and that is the direction is 63.4 degrees. Anytime the question is going to ask about a force, it should have a magnitude and direction. Then this is for this piece of magnetic forces and magnetic fields. And I'm going to also add more videos for this material. Thank you.